Assalamualaikum warahmatullahi wabarakatuh and very good day to my respectful friend. My name is Muhammad Zakaria with matric number CN190122. My Bachelor Supervisor is TS Dr. Nasrul, Fikry Bencik Pak. Regard for today's presentation, I would like to present my proposal for my Bachelor degree project, which is titled Production of Bioethanol from Bamboo Powder via Sodium Hydroxide-Dilute Sulphuric Acid Pre-treatment. Throughout my studies, a guided outline had been created to complete the project. Hence, in this presentation video, I would like to present 5 chapters that are included in my studies. For the first chapter, the introduction of the project is discussed. In this chapter, the background of the study, problem statement, objective, scope and significance of the study is further elaborated. For the first subtopic, I will discuss the background of the study. As we all know, biofuel is a new type of fossil fuel that is derived from biomass waste and has the potential to replace commercial fossil fuel. In that case, biofuel is recognized as a renewable energy. The 3 major biofuel feedstock groups are cellulose biomass, sugar, and starchy crops, as well as oil-producing plants. Most of the research prioritize cellulose biomass compared to other groups since it does not conflict with human food production. Lignocellulosic biomass or LCB has the potential to become a new source for biofuel production since it is easier to find as well as has the cheapest feedstock for the production of biofuel. Moreover, the high composition of cellulose and hemicellulose in LCB make it suitable for becoming biofuel feedstock. However, LCB needs to undergo various stages to produce bioethanol. The pretreatment stage is focused on this study. Pretreatment of LCB is important to prepare LCB for enzymatic hydrolysis and fermentation stages to maximize the production of bioethanol products. Cellulose and hemicellulose will turn into simple sugar before the fermentation process. In this study, bamboo from Caesareum grande species is used. The reason I use bamboo is that it has short maturity period, which is around 3 to 5 years and contain high cellulose content. The problem statement for this study is the complex structure of the cellulose and hemicellulose, which inhibit the enzymatic activities toward the lignocellulosic substrates, which result in a low hydrolysis rate. Hence, recrystallization of cellulose is necessary. Furthermore, the destruction of lignin is difficult due to its rigid structure. Lignin prohibits microbial and pathogenic attacks toward the lignocellulosic substrates. Thus, delignification is needed to increase the rate of enzymatic digestibility. For the last point, the cost of the pretreatment becomes a challenge since a large amount of enzyme is needed to degrade the polysaccharides. Therefore, the objective of the study are to observe the effect of sodium hydroxide and dilute sulphuric acid pretreatment on the structure of lignocellulose in bamboo powder, to compare the composition of cellulose, hemicellulose, and lignin between untreated bamboo powder and treated bamboo powder, and to study the effect of different concentration of sulphuric acid on the amount of bioethanol produced. The scope of the study is first, the bamboo powder is treated with sodium hydroxide solution with 1:10 ratio and sulphuric acid solution with a concentration of 0, 1, 2, 3, and 4. The structure of lignocellulose of bamboo powder for each treatment was determined by using X-ray powder diffraction, Fourier transform infrared spectroscopy, and scanning electron microscope. Second, the Chazen method is used to analyze the composition of cellulose, hemicellulose, and lignin in untreated bamboo powder and alkaline acid pretreatment bamboo powder. Third, the pretreated bamboo is added to solution media with a ratio of 1:10. The solution is placed in autoclave. Cellulose enzyme and Saccharomyces cerevisiae are added into it. The fermentation process occurs at different resident time, which is 72 hours, 96, 120, 104, and 168 in the incubator. The amount of bioethanol produced is determined by using gas chromatography. The percentage yield of ethanol is calculated by using a formula. The significance of this study is the discovery of LCB has a new source of biofuel may contribute to less uses of fossil fuel in the future. The double-stage pretreatment helps in increasing the accessibility of enzyme towards the lignocellulosic substrate. Ideally, the combination of alkaline and acid pretreatment is proven to increase the production rate of bioethanol as well as overcome the limitation of each pretreatment. Thus, this is the best hope that the proposed sodium hydroxide dilute sulphuric acid pretreatment succeed in overcoming the barrier for lignocellulosic biofuel as well as fully utilizing the potential of bamboo. In Chapter 2, I will focus on literature review of this study. These are the subchapter contained in Chapter 2. For the introduction of biofuel, as I mentioned earlier, biofuel are produced by using biomass-based renewable sources such as animal, byproduct and plants. Biofuel have the same characteristics and properties as conventional fuel. Biofuel technologies are classified into conventional biofuel and advanced biofuel. Conventional biofuel is produced from eatable crops and is called first generation biofuel. However, there is an issue with this generation since it competes with the human food supply for biofuel feedstock. On the other hand, advanced biofuel is produced from agricultural waste and non-food grow feedstock. Advanced biofuel consists of the second, third and fourth generation, in which each generation have different techniques and process to produce biofuel. For the interaction of LCB, LCB is synthesized from the reaction of carbon dioxide and water via the photosynthesis process. LCB is considered the most abundant biorenewable resources that existed. LCB is divided into biomass, virgin biomass, and energy crops. Bushes and trees fall into biomass categories, while bagasse and agricultural waste are categorized as virgin biomass. Generally, energy crops are chosen as biofuel feedstock for the second generation since they have high biomass productivity. There are two ways to synthesize LCB into a biofuel, which are biochemical process and thermochemical process. The main component of LCB consists of cellulose, hemicellulose, and lignin. Cellulose maintains stability and enhances the mechanical strength of the fiber. It contains a high polymerization degree due to glucose rings. Hemicellulose is a hydrophilic molecule that is soluble in alkali. It has an amorphous structure and low polymerization degree, unlike cellulose. Lignin consists of phenyl propane unit and is categorized as an amorphous and phenylic macromolecule. It has higher resistance compared to others. Those features are the chemical structure for each group. For the interaction of bamboo, bamboo is part of the forest and plant resources in the world. Bamboo is typically grown in tropical and subtropical zone. Sometimes it grows in frigid and temperate zone. Bamboo is considered one of the main resources for non-timber forest products since it has high economic value and a short rotation period. This table shows the major producer of the bamboo in this world. For the vegetative growth of bamboo, bamboo is labeled as one of the fastest growing plants since it can grow 10 to 30 meter in just 40 to 60 days. Moreover, it can reach its maturity in one season. Bamboo is divided into two types, which are sympodial bamboo and monopodial bamboo. Bamboo can reach its optimal material properties in 4 years. This table shows the difference between the growth characteristics of bamboo and trees. For the chemical characterization of bamboo, the main components are almost similar to other LCB, which is cellulose, hemicellulose, and lignin. The composition of this component depends on the condition of the growth, age, part of the stem, and species of the bamboo. Usually, bamboo contains 60% to 70% of hollow cellulose and 20 to 30% of lignin content. For this subtopic, I will expand on existing pretreatment process of LCB and the chosen pretreatment. There are 4 types of pretreatment. First, physical pretreatment is the method where the particle size of the LCB is reduced or the structure is disturbed to increase enzymatic hydrolysis. Second, chemical pretreatment is the method where cellulose is degraded, causing its crystallinity index to decrease. It also reduces the hemicellulose and lignin content in the LCB. Third, physiochemical pretreatment is the process LCB is treated at high temperature and pressure. And lastly, fourth, biological pretreatment is the process where the lignin component is removed by using a specialized enzymatic system. The chosen pretreatment for this study is alkaline acid pretreatment. The bamboo powder is treated with both alkaline and acid. Normally, alkaline pretreatment is performed at low temperature, while hydrolyzation of cellulose in acid pretreatment is operated at high temperature. Both of these pretreatment disrupt the structure of the LCB to increase the enzymatic accessibility to the lignocellulosic substrate. Simultaneous saccharification and fermentation (SSF) is a process where enzymatic hydrolysis and fermentation is done at the same time in one reactor to achieve value-added products. Cellulose is hydrolyzed by an enzymatic complex to produce sugar. The sugar are then fermented by the microorganism to produce biofuel. These processes are performed in one place at the same time. The design of the experiment for this project is a 6x5 design of a full factorial experiment since there are two variables. Hence, 30 experiments need to be conducted. The table shows the potential combination of the experiment. The statistical analysis used for this study is ANOVA, F-test and correlation analysis. In ANOVA, the p-value is compared with the significant level, while F-test identified the best statistical model. Correlation analysis show the linear association strength between two variables. In this chapter, the methodology of the study is discussed. For the preparation of bamboo powder, the bamboo clump is immersed for 1 day in the tap water. Then, it is subjected to dismill 2 times with a 0.5 cm disc cap and 35% consistency. After that, the bamboo is loaded into a twin screw extruder to produce a bamboo powder. For alkaline acid pretreatment, alkaline pretreatment is done in the first stage. Bamboo is treated with 5% concentration of sodium hydroxide solution with a ratio of 1 to 10. The mixture is stirred in a rotary air bath in an incubator for 1 hour at 120 rpm and 85 degrees Celsius. The mixture is filtered and separated into two fractions. Acid pretreatment is done in the second stage. Bamboo powder is treated with dilute sulphuric acid at different concentration with a ratio of 1 to 10. The mixture is processed in autoclave reactor at 121 Celsius for 90 minutes. The slurry solution is filtered and separated into two fractions. The solid fraction is treated in autoclave for 30 minutes with 100 ml of 4% concentration of sodium hydroxide. The slurry solution is filtered and separated into two fractions. The pH value of the solid fraction is neutralized and hydrated in the oven at 105 degrees Celsius. Next, the bamboo powder will be analyzed by using the Chaser method, XRD, FIR and SEM to study the structure of the bamboo powder. Then, the bamboo powder will undergo simultaneous saccharification and fermentation. The bamboo powder is added to the media solution containing yeast extract, ammonium sulfate, dipotassium sulfate, epsomite and calcium chloride with a ratio of 1 to 10. The solution is placed in an autoclave for 60 minutes and then let it cool. 3 ml of cellulose and 5 ml of Saccharomyces cerevisiae is added. Fermentation occurs at different residence time in an incubator at 37 Celsius and 120 rpm. At the end of the experiment, the bioethanol will be analyzed by gas chromatography and ethanol yields. These are the materials and apparatus used in this study. And these are the chemical substances used in this study. For Chapter 4, the expected result for this study is discussed. From this study, it is expected that the inert content in the untreated bamboo powder and alkaline pre-treatment bamboo powder is higher than alkaline acid pre-treatment bamboo powder. Other than that, the pre-treated bamboo powder is expected to have a small particle size. Next, the crystallinity index for alkaline acid pre-treatment bamboo should be lower than other samples. Furthermore, there are changes to the peak intensity of pre-treated bamboo powder functional groups. Moreover, alkaline acid pre-treatment bamboo powder should produce a high concentration of bioethanol. Lastly, the percentage yield is high for alkaline acid pre-treatment. In conclusion, this work proposed the study of the effect of sodium hydroxide dilute sulfuric acid pre-treatment of bamboo powder on the production of bioethanol. This method is effective in spreading hemicellulose and lignin, resulting in a high percentage yield of ethanol. The pre-treated bamboo powder is characterized by using the Chaser method, SRD, FTIR, and SEM, while the ethanol is analyzed by using GC. Hence, this study hopes that it will give a piece of knowledge on the new pre-treatment for bamboo. There are some of the references used in this study if you are interested in this study. That's all from me. Thanks for listening.